I've been trying to reach for an online class with you for a long time. So my suggestion will be the first bit of the work of the unit is theoretical. And therefore, these are things you can read and be able to understand, so that you allow me to move to some of the topics or subtopics that are more mathematical. And in that regard, then the first topic is on the introduction to analytical chemistry. The first thing is to define what is analytical chemistry. Being one of the branches of chemistry. And then there's a bit of application. It has a wide application in so many other fields, which I think you can be able to see from the notes. So it's an area which it is applied in all the other branches of chemistry, in biochemistry, clinical medicine, pharmacy, and so on, because it entails a bit of analysis. And you know, any other branch of chemistry will be doing some analysis, even if it is physical chemistry. So if that is understood, then I wanted to show you the topics and the subtopics. So I think we are in the very first page. So I'll leave the introduction. You spend few hours or few minutes, depending on the speed of revising. You go through it. But most importantly is that in the first bit, there is this analysis that is referred to as trace analysis. Trace analysis is where you are doing analysis at a very low concentration. They are told at microgram level and below. So such analysis, we are told it is facing many challenges. So I want you to identify those challenges. We are told one of the main is interference. Then the other one is contamination. Then the other one is loss of the sample. So because you analyze in very low concentration, you find that the analysis is subject to a number of problems. So I think that is what you can see the wide application. And then we scroll. Want to go to this trace analysis. So the three major challenges are those that I mentioned: contamination, interferences, and then sample loss. Now, because of those challenges, then when you are performing such a analysis, then you should be able to try as much as possible to minimize those challenges. So when we talk of interference, we are talking of presence of other compounds that can be analyzed by, can be detected by the method that you are using, and therefore they give erroneous results. So these are different compounds that are present, but your technique that you are using is able to detect. So we say they tend to interfere. And therefore they need to be removed before you do the analysis. So they are actually known from theory that a certain compound is likely to interfere the analysis of a particular analyte. Like I think you are told here that lead, when you are using diatisone, compounds such as zinc, cadmium could actually react with their reagent to obtain inaccurate results. So it therefore calls that before you do your analysis, you need to understand what are some of the challenges or some of the interferences for a particular analysis, so that you tend to remove them before the actual analysis. Then contamination, on the other hand, is about presence of the analyte coming from elsewhere during the analysis. The elsewhere that we are talking about here will include storage containers, working apparatus, and even the reagents. You remember, when you are doing analysis, we always prepare our samples. Now, during the preparation, you have containers to store. We have containers to collect your sample and so on. So they can bring in the analyte. So that when you are doing the actual analysis, the analyte, some part of the analyte will be coming from those sources. Again, you might be using several reagents here and there during the preparation. Those reagents might contain your analyte, and therefore it will contribute to the concentration that will be present when you do the determination. So again, there are some of the ways that can be put in place to minimize, such as using a specific containers for specific compounds, doing what we call blank analysis. Blank analysis is that you get something that you can subject through the entire process and see whether there is the analyte. For example, the reagent that you will be using, maybe you need to know whether it contains the reagent, the analyte of interest. If it contains, then it means in your final result, you need to subtract. But ideally, you expect not to contain. So that is how you can minimize, so that you know from your reagents of your solvents, this is the amount of the analyte, and therefore the correct concentration will be obtained by subtracting what was in the blank. So that is another way. So use of specific containers for specific compounds. There are some containers that they can produce the analyte, or they can react with your analyte. Like we are told that for polythene bottles for mineral ions, and then use glass bottles for organic compounds. You can use glass bottles for mineral ions, right? All right, and then the other way is to get reagents that are of specific standards, and this is meant just to estimate impurities. So you find when you are doing the very serious analysis, especially trace analysis, you use standards, reagents that are very pure. So these ones are the analytical grade reagents. Then the other challenge, I think, you are told sample loss. It is common in trace analysis, and this can be as a result of sticking on the walls of the container and so on. Right. So I think then the other things are theoretical. Then in the next topic, that is on steps of analysis, I think this one outlines the major steps that you follow in any analysis. Of course, analysis is divided into two. We have got a qualitative analysis, and then we have got a quantitative. Qualitative is identification of the components present. Uh, Quantitative is determination of the amount of a particular analyte in a given sample. Here you are talking of relative quantities. Now, but either way, whether it is qualitative or quantitative, it follows a very 5 steps which you are given. We get the sampling, you do the pre-treatment, you convert it to a measurable form, then you now measure. That is now you subject to the actual analysis in the lab, and then you do the calculation and finally interpretation of the data. So any kind of analysis will follow those 5 steps, and I think the module is able to give a detail for each step. So, like sampling is about collection. You obtain the portion of the substance that you want to analyze, but you consider the factor so that whatever you get is actually a representative of the substance that you want to analyze. So at times you might have to mix here and there. At times you need to collect several samples and then mix them, and so on. We have been given 2 types of sampling techniques. There is what we call random sampling, and then there is what we call statistical sampling. So as you go through the first step on the sampling, make sure that you are able to get the distinction between the sampling techniques, the random and the statistical. So of course, statistical means you follow some setup statistical theory or formula, while for random, as the name suggests, is that it gives a chance for each part to be considered as part of the sample, Right. So I hope we are. Then now in the sample pre-treatment, it's about once you get your sample, you perform some treatment to ensure that your sample is stable or it is in the same form as you collected, awaiting analysis. Because you might, where you are sampling your analyte might not be very near to the lab, so you need to transport and so on. So there are some samples that once you collect it from their source, they might interact with the atmosphere and form other compounds. So what you need to do is that you perform what you call sample pre-treatment to ensure that your samples are stable, are in the same form until awaiting analysis. So the objective here is to make sure that your samples are in the same form. There is no loss, there is no decomposition along the way. So again, that is mentioned. Then conversion to measurable form is that you convert your sample depending on the instrument that you will be using. Some might be you are collecting a solid, but the instrument requires a solution or a liquid form. So you need to dissolve. Some require that your analysis is done on a gaseous form. So here you need to convert it to gaseous form. So such steps is what we are saying. It is where you are now converting your sample into a form that can be measured. So depending on the instrument that you are using. So sample preparation will involve several ways depending on exactly what you are analyzing. Then the measuring is subjecting them to the actual measurement using the various techniques, the wet methods, the instrumental methods, or even the classical method. So depending on which analysis you are doing. So measuring the analysis is the actual measurement. But as you measure, of course, we said when you measure, you are getting quantities. If it is a quantitative analysis, you are getting values. Then you need to interpret those values. If we are doing replicates, of course, we normally do a lot of analysis. We don't do one, we do several. So once you get the various results, then maybe you might need to do some statistics here and there. You might require to do the mean or the average times. Others you need maybe standard deviation. You might require to perform a standard deviation. And so the calculation involved depends on the actual results. Depend on the actual results and also depend on the use of those results. Now, interpretation basically means giving meaning to your results. Because whatever you're obtaining might be figures. You want to see what are these figures mean. If it is you are getting the acidity or the basicity of some substance, then you will get values. You will get 4, 5, 6, between 1 and 14. So what does that mean? So if you get a pH of 13, you know that is basic. If you get a pH of 4, that means acidic. So that interpretation is what is the last step in any analysis. If it is infrared, you are getting the functional groups. You get a certain frequency, so using the reference or you can be able to tell that this frequency implies this kind of a functional group. Is it an OH group? Is it a carbon-carbon group? Is it a carbon-nitrogen and so on? So from those chromatograms, you can be able to do the interpretation and basically suggest that maybe a compound is is uh, is made up of is it an alcohol, an alkane, an alkene, an alkyne, and so on. Right. So I think right then the next discussion is that let me see whether it is clear in the notes. The next thing, I'm just brushing through the theoretical units, topics to just mention the areas of interest. Now, the other thing is that there are errors in chemical analysis, and I don't know whether the notes are very clear for this. Uh, So we are told that any kind of practical, any kind of analysis is subject to errors. There'll always be errors, even if we are so keen in performing the analysis. So any type of analysis or any type of measurement is always subject to errors. And that these errors are classified into two. I think the notes is not very clear. You need to check on these types of errors. We have two types. So they are classified into two. We have what we call random errors, and then we have what we call systematic errors. Now, random errors, they are also referred to as indeterminate. And these are errors that will actually occur uh, always in our results. They occur randomly. They are actually, you cannot be able to identify their sources, but they are always present. And some of the contributing factors to these errors are changes in environmental conditions, things that you don't have control over. So they are referred to as random errors, and actually they are also known as indeterminate errors. They are errors that you don't have control over. You don't have the capacity to minimize them because either way you are not able to identify their source. So they'll always be present. So those are random errors. Then there is systematic errors, which are referred to as determinate. These ones, they are errors that you can identify and will actually cause your results to deviate in a certain direction. So they are unidirectional. You can have the results increasing slightly or decreasing slightly consistently. So you have results that are actually below the average or below the expected, the true value. So they are unidirectional. Their causes could vary from the analyst, from wrong calibration, faulty instruments, and so on. These are things that you can be, once you are able to identify, you can minimize. So they are referred to as systematic errors. Now, the other thing about these systematic errors is that, as I said, they are unidirectional. They can either be slightly more than the true value or slightly less than. So they actually affect the accuracy. They affect the accuracy of the result. While the other one, because it can either go in any direction, the random, it affects the precision. It affects the precision of result. So check those notes on the systematic and then random errors. Okay. And then there are of course suggestions on how to go about reducing or minimizing some of these errors, like systematic errors. You need to minimize. Now there is given the results, you can be able to estimate or make a comment on the accuracy and the precision. So here, we need to perform a bit of statistics, and one of the statistics that you'll perform or that you'll perform on Sunday, so that you're able to make a decision on whether there was systematic errors or random errors, is that you perform the range. That's the difference between the lowest and the largest value. Then the other thing that you do is that you do the mean, that is the average, and then lastly that you do the standard deviation. Now, once you have those, the mean will actually be used to compare how close the mean or the average is to the true value. So when the results are very close to true value, we talk of, when the average is very close to true value, then we talk of accuracy. The results are a bit accurate. I don't know that, are you still seeing the notes? Hello?
Oh, you cannot see.
It
Yes,
does
sir.
disappear.
Yes.
But you are able to hear me. Let me reshare then. Let me share. So I was saying that you perform the range, standard deviation, and the mean is used to check the accuracy, while the standard deviation and the range are actually used to check the precision, right? Now, the range, as we know, the difference between the largest value and the smallest value is that that one will give an idea of how close these results are, how close to one another, how they agree with one another. If the range is small, and if the standard deviation is also small, which they go hand in hand, it will actually imply that your results are precise. But if it is large, then it will imply your results are not precise. Similarly, for the mean, if it is near to the true value, then it will imply that your results are accurate. But if it is far away, if the mean and the true value is far away, then we talk of inaccurate results. So I think there's an example in the notes, and you can always be able to check, to go through that and see how they do the comments on the accuracy and the precision. But as I said, precision, we check using the range and the standard deviation. Then the accuracy, you check with the mean, how close the mean to the true value. But as we do the standard deviation, I think it is captured in the notes that the formula is not the same as what we normally use for mathematics, where you divide, you have the summation of the deviation square, then divided by
Sir, we are not hearing you.
I can't hear you. Usili huko. Niko hapa na sisikii kitu.
Lecturer ametoka.
Somebody to inquire. Amecommunicate. Bwana.
Hello guys, exam zinaanza lini?
Alafu hizo notes zimeuploadwa hapo kwa system, kuna part zingine hasionekani vizuri.
Click lessons. The notes are really visible. The lessons, each lesson, you just click by one.
Naitwa Nanti.
Dennis. Dennis.
Yes?
Class.
Yes? Yes?
Class imeisha ama imeendaje?
Hata mimi nangoja, lakini lecturer amecommunicate hapo kwa chat akasema ako na shida ya network.
Sawa.